We start every day, and, probably without even a second thought, we're entrusting our lives to these enormous high-speed machines, these massive steel systems moving across incredibly complex networks. We're talking, of course, about rail. And while maybe aerospace engineering often gets the spotlight for safety rigor, the fact that we trust trains, sometimes running at hundreds of kilometers per hour on shared tracks, often just feet away from the public every single day. Well, it's a profound testament to some kind of invisible process, isn't it?
It really is.
That collective trust, it's absolutely earned. But how? How is that trust formally engineered? How do you make sure that when you integrate something new, say a futuristic software-driven communications-based train control system, or maybe just a brand new maintenance policy, how do you ensure it integrates safely into this sprawling, sometimes century-old network?
Yeah.
That invisible, rigorous, systematic process. Well, that's what we're going to dive deep into today.
That's exactly right. Today, we're really dissecting system safety assurance, or SSA as it's known. Now, if you're an engineering student, maybe an early career professional, or frankly anyone involved in planning or deploying rail technology, SSA is, well, it's the foundational language of your career.
Okay.
It is the comprehensive governance framework. It's not just like a collection of processes. It is, and this is crucial, the methodology for generating the objective evidence. That's the key phrase. The evidence needed to satisfy everyone involved, regulators, investors, the public, that any change, big or small, hardware or policy, can be safely integrated and operated.
For objective evidence, got it.
And the whole mission of SSA, it's driven by a fundamental legal duty, ensuring safety so far as is reasonably practical, or SFAP. We're definitely going to spend some time unpacking that SF concept because, honestly, SFAP is the core difference between just compliant engineering and truly safe engineering. SSA is the practical tool set you use. It helps you transition those theoretical design specs into verifiable, consistent safety across, well, one of the most complex interconnected transport systems on the planet.
That makes sense conceptually, but let's push back a bit straight away.
Yeah.
You said SSA isn't just a regulatory hoop to jump through. But I can imagine for a young engineer facing intense project deadlines, budget pressure, SSA might feel like nothing but complex paperwork. Why is it so essential they see it as a genuine practical structure, not just, bureaucratic overhead?
Because if you don't use a structured assurance process, the entire project, and let's be clear, potentially the lives it impacts, is fundamentally vulnerable. Without SSA, you're essentially relying on siloed, maybe localized knowledge. And with modern rail complexity, it's a recipe for catastrophic interface failure.
Okay, interface failure. Let's dig into that.
Correct.
Okay, let's unpack that need for structure then. Rail transport didn't always need this level of complex governance, did it? I mean, back when you had steam engines, mechanical levers, safety assurance was probably simpler, more localized, maybe more mechanical.
Yeah, much more direct.
So what changed? What forced the industry to adopt this kind of dedicated, structured SSA framework?
The big change was the integration revolution, really. Those traditional siloed safety approaches where the track guys did their thing, the signal guys did theirs, they just stopped being effective when everything started connecting.
Right.
A modern railway system is like an organism of integrated elements. You've got highly sophisticated rolling stock, complex traction controls, all communicating with advanced, often wireless signaling systems like communications-based train control, CBTC.
CBTC, that's a big one.
CBTC is the perfect example, really, of why SSA is non-negotiable now. Think about traditional signaling. It relied on physical track circuits, fixed block sections. The failure modes were, well, relatively understood, mechanical, electrical. But CBTC, it uses digital communication, constant calculation of safe separation distances based on real-time data. This relies on stable, high-speed data links, incredibly robust software integrity, and perfect coordination with the train's braking system. A single software glitch, maybe a blip in the telecom link, that can instantly compromise safety across multiple traditional engineering disciplines.
So SSA really emerged because the old way of checking things just couldn't handle those system interfaces. The risk doesn't just add up anymore. It sort of multiplies exponentially at those connection points.
Precisely. That's it, exactly. SSA provides the oversight. It ensures that if, say, the software in the train control system needs input from the onboard GPS unit, and that GPS unit relies on a specific telecommunication link, well, all three disciplines have coordinated their hazard analyses. They've defined their safety requirements consistently.
Oh, okay.
It stops a failure in one little corner from cascading unpredictably across the whole network.
Now, we often hear rail is incredibly safe, especially when you compare it to, say, road travel.
It generally is, yes.
But the statistical reality, it still gives a pretty stark look at where the risks do persist and maybe why the system-wide assurance matters so much.
Yeah, the data is really illuminating because it shows where current safety systems are succeeding brilliantly, but also where the major challenges still lie. If we look at the U.S., for instance, in 2023, there were nearly 1,000 railway fatalities reported.
Wow.
But, and this is the critical context for safety engineers, a huge majority, something like 71.9%, involved trespassers. Now, that's not primarily a mechanical failure risk in the traditional sense. That's an interface risk, the boundary between the railway operation and the community.
Okay, that's a key distinction.
It is. And similarly, if you look at data from an Australian network, say between 2016 and 2024, of 744 fatalities, around 85% were sadly suspected suicides. That leaves about 115 operational fatalities over those 9 years. Again, the takeaway for our audience isn't just the tragedy of those numbers, but the specific engineering challenge they represent. Where are those operational risks coming from?
And I guess the flip side of that data proves that internal safety management systems, the ones focused on employees, seem to work exceedingly well.
Absolutely. The massive success story that really validates SSA and robust safety management systems, or SMS, is employee safety. In the U.S., in 2023, I think the number was only 7 on-duty employee deaths across the entire country's rail network.
That's incredibly low.
It's phenomenally low, and it proves that when the railway has direct control over the environment and the processes through these structured systems, it works. The systematic processes are highly effective at protecting staff.
So the big remaining persistent challenge, the one that SSA has to constantly address, it isn't so much internal operational breakdown anymore, but managing those boundary conditions, the interface risk, as you called it, between the high-speed system and the human world-level crossings, unauthorized access, platforms, that kind of community interaction.
That is the substantial focus area moving forward, yes. And this is where engineering controls start to intersect really heavily with operational policy, and increasingly with technology too. Things like predictive analytics for identifying, say, unauthorized access hotspots. SSA has to ensure those interface controls, whatever they are robust and constantly monitored for effectiveness.
Now let's talk economics for a second. Safety is often, perhaps incorrectly, categorized as just a cost center, something that doesn't generate revenue.
Right, the necessary evil view.
Exactly. But your sources, or rather the evidence, shows that investing in SSA and the safe infrastructure that results from it is actually a massive economic driver. How do you make that case to someone holding the purse strings?
You argue with the multiplier effect. It's quite compelling. Safety isn't just about preventing negative outcomes. It's fundamentally about investment protection and enabling reliable service. Research, particularly in the UK, clearly demonstrates that every single pound invested in rail infrastructure generates something like £2.50 in broader economic activity.
2.5 times. That's huge.
It is, and it comes because the inherent reliability and trust that safety generates allows the system to function efficiently.
So where exactly do those economic benefits come from? How does that £2.50 actually materialize?
Well, they flow from several key areas. The most immediate is probably user benefits faster, more reliable journeys, reduced costs for commuters, for freight shippers.
Yeah.
Then you have massive external benefits like easing congestion on parallel road networks. That alone is huge.
Yeah.
The UK rail network, for example, is calculated to deliver something in the region of 31 billion annually just in these broader benefits, congestion relief, productivity gains, wider economic impacts, and that's all underpinned by it operating safely and reliably.
Wow, 31 billion.
And this reliability, which is fundamentally assured by SSA processes, it creates jobs too. The rail industry has a significant employment multiplier. One railway job, it's estimated, can create nearly 4 additional positions. I think the figure is 3.9 in supporting sectors like manufacturing, logistics, technology. So safety assurance isn't a cost, it's the economic foundation. Without that demonstrable assurance, investment confidence disappears, and these massive economic benefits simply wouldn't be realized.
That shifts our focus perfectly then to the sheer scope of SSA. If it's responsible for maintaining the operational integrity that drives billions in economic activity, it must be pretty comprehensive. Let's start with its primary mission, standardization, or what you called harmonization earlier.
Yes, harmonization is the key goal. The primary objective is to establish a harmonized, uniform, and consistent approach to safety management. And that's across every asset, every system, whether it's brand new or legacy infrastructure already in place. SSA exists fundamentally to solve what we often call the fragmentation problem.
Okay, the fragmentation problem.
Yeah.
Can you explain that in a practical sense? What does that look like on a real project?
Yeah, absolutely. Imagine a large rail project. You might have 5 major players involved. Maybe the state-owned infrastructure manager who owns the track, a private train operating company running the trains, perhaps a signaling contractor from France, a rolling stock manufacturer from Germany, and then a local construction company doing the actual civil works like bridges and tunnels.
Okay, a typical scenario.
Right. Now, if each one operates under its own safety standard, even if each standard is excellent on its own, but they're all slightly different, where do the inevitable safety gaps appear?
At the joins.
Exactly. They appear at the interfaces between these players. We often joke in the industry, the signaling team might not realize the civil team adjusted the track gradient by just 0.5% over here to manage drainage. Seems minor, right? But that subtle change could suddenly invalidate the braking calculations for the new high-speed train, which relies on perfect track geometry data. SSA demands that these fragmented entities coordinate their hazard logs, their safety cases, their procedures flawlessly. It's the framework that forces all these different languages of rail engineering to speak a common safety language.
And this framework, this common language, it needs to be scalable, right? You can't possibly apply the same multi-year, full-blown SSA process to, I don't know, changing the wording on a platform sign.
Precisely. That would be ridiculous.
Yeah,
The governance activities absolutely must be scalable and tailorable. The complexity of the assurance process has to match the complexity and the criticality of the change being made.
makes sense.
So a minor modification to, say, an operating rule might just require a swift, streamlined assurance activity. Document the change, assess the impact, done. But the construction of a major new rail line, integrating multiple new technologies, that demands the full V-model lifecycle management approach, probably a multi-volume system safety case documenting everything. It scales up significantly.
Okay, let's get a bit more granular then about what SSA actually covers. Because when we talk about railway infrastructure, we're talking about massive interdependent systems. Can you give us the main technical categories it applies to?
Sure. We can probably break it down into 5 really big areas where SSA must be applied rigorously. First up, you've got rolling stock. This covers everything that moves on the rails: locomotives, passenger carriages, freight wagons, even those specialized maintenance vehicles you see out sometimes. The key assurance areas here are things like the complex traction systems, how power is delivered, and controlled braking systems, which can be complex, blended pneumatic and regenerative systems now.
Regenerative, yeah.
And, of course, the structural integrity of vehicles themselves, including crash-worthiness standards, how they behave in an impact.
Okay. And then the power that makes it all move.
Next, electrical systems. And this is broader than just the overhead lines or third rail providing traction power. It includes auxiliary power for all the onboard systems, lighting, platform systems, and, crucially, with regenerative braking becoming more common where trains feed power back into the network, that introduces new system stability risks that absolutely have to be assured, an electrical fault can become a safety fault instantly.
Right. Then the communications.
Third, telecommunications. Often invisible, but utterly critical now. This covers everything from the old-style analog voice communication for drivers right through to the high-speed digital data transmission needed for modern train control systems like CBTC. And it also includes passenger information systems, emergency response networks. If that high-speed data link goes down in a CBTC system, the whole signaling system essentially fails safe, but the operation stops. So safety assurance for the comms network is intrinsically part of overall system safety.
And that brings us, I guess, to the safety epicenter, signaling systems.
Undisputedly, this is probably the most safety-critical category. SSA covers the entire spectrum here, from legacy mechanical interlockings, the old levers and rods, right up to modern computer-based interlocking, or CBI. Then there's automatic train protection, ATP, which enforces speed limits automatically. And of course, the cutting-edge stuff like communications-based train control, CBTC.
And the challenge here is the software, right?
Hugely. Because these modern systems are so software-driven, SSA has to focus intensely on software integrity, proving the code does what it says it does, redundancy verification, making sure backup systems work, and increasingly, cybersecurity assurance. That's a significant difference from the old mechanical era.
Definitely. Okay, what's the 5th category?
Finally, you have the foundational elements, the civil infrastructure. This is the tracks, bridges, tunnels, stations, platforms. And people sometimes underestimate this, but even a seemingly simple civil modification, maybe adjusting track curvature slightly or modifying a platform edge profile, requires a full SSA assessment. because it changes the inherent safety parameters of the system, or it changes that interface risk with the public or the rolling stock.
That comprehensive coverage, it really suggests SSA has extended its reach beyond purely operational safety, preventing collisions or derailments into adjacent risk areas too, like the digital environment and just basic system reliability.
Absolutely. While the primary function, the core job, is preventing those operational incidents, its scope definitely extends. For example, preventing environmental damage is often a key consideration now. A major train incident causing, say, a large fuel or hazardous cargo spill that requires specific safety assurance controls to mitigate that potential outcome.
And cybersecurity, you mentioned that with signaling.
Yes, and it's critical across the board today. SSA must encompass cybersecurity. In a digital railway environment, a cyber attack that, say, manipulates signaling data or disables a remote monitoring system, well, functionally, that is a safety incident waiting to happen. So we have to assure the resilience of the digital envelope just as rigorously as we assure the strength of the steel rails.
So does that mean system integrity also includes assuring reliability, availability, and maintainability, the RAM metrics?
That's correct. RAM performance is intrinsically connected to safety. Think about it. An unreliable system, one that frequently fails and requires maybe emergency manual intervention by staff, is inherently less safe than a highly reliable, predictable system. That operational complexity, driven by unreliability, increases human factor risk mistakes are more likely. So SSA treats RAM performance as a key input to the overall safety case. You need to show the system is reliable enough to be safe.
But there is a crucial distinction here, isn't there? Something that often trips up newcomers. SSA focuses on system-level risks, but it seems to have a hard boundary it respects. It doesn't cover the day-to-day management of workplace health and safety, like a construction site safety plan.
That distinction is absolutely vital to understand. SSA is concerned with the functioning of the railway system as a whole, as an operational entity. It specifically excludes the detailed workplace health and safety WHS standards that apply during, say, construction or routine maintenance activities. Things like fall protection for workers, scaffold integrity checks, manual handling protocols, those are managed under a separate WHS framework, often by different teams and regulations.
Okay.
SSA's job is to ensure that the finished or modified railway machine itself is safe to operate and interact with. It's not there to police the safety standards of the workers who build or maintain it, although obviously the two are related.
All right, different focus. And finally, a really interesting point. SSA isn't just about the hard assets, the trains, the track, the signals, which is maybe a key point for people in management or operational roles who might not be, swinging a hammer or writing code. It applies equally to changes in rules and procedures.
It absolutely does. It applies to organizational and operational changes if they interface with safety-critical activities. Think about changing a maintenance procedure. Let's say you want to extend the inspection interval on a critical component from every 6 weeks to every 8 weeks to save costs.
Okay.
That change requires an SSA process. You need to provide the evidence to demonstrate that the new, longer interval is still SFIRP, still acceptably safe. The same applies to revising operating rules for drivers, changing staffing levels in control centers, or altering the business processes used for incident response.
Oh.
If it touches safety, it needs formal assurance.
Okay, this brings us nicely to the conceptual heart of this whole assurance structure. How safety itself is defined, particularly as dictated by the law. Every rail transport operator, or RTO, faces this really stringent legal duty of care. How does SSA help translate that sort of abstract legal duty into tangible engineering requirements on the ground?
Yeah, the legal obligation is the absolute non-negotiable starting point. Laws like the Rail Safety National Law in Australia or similar frameworks you find globally, they require every RTO to establish and maintain a robust safety management system, an SMS.
Right, the SMS.
The SMS is essentially the organization's documented promise to manage safety effectively. SSA, however, is the structured technical and engineering methodology you use to demonstrate continuous compliance with that promise. It's the how-to guide for fulfilling the SMS commitments.
Okay, so the SMS says what you'll do. SSA shows how you do it and proves you did it.
That's a good way to think about it. And crucially, the law dictates that the ultimate duty of care is retained by the RTO. It cannot be outsourced or transferred. So if you hire a third-party contractor to design, say, a new signaling system, the RTO still holds the final legal responsibility to ensure that integrated system is safe.
Ah.
This makes SSA, which structures that demonstration of safety, a mandatory operational requirement right from the boardroom down to the component-level engineer. You can't delegate the ultimate responsibility.
So the law says you must manage risk, and this term SFARP, so
Yeah.
far as reasonably practicable, it defines the boundary of how much risk management is considered enough. Let's really tackle this concept, SFARP. You mentioned it's the ultimate balancing act. For an engineer facing a specific design choice, how does SFARP practically guide their decision-making? What does it tell them to do?
Well, SFI requires the duty holder, the RTO, or anyone acting on their behalf to systematically reduce risks to the lowest level that is reasonably achievable. The concept really pushes beyond simple engineering compliance, where you might just check off a minimum standard in a rulebook. It demands continuous risk reduction.
Okay.
The balancing component comes in, where you have to weigh the benefits of putting in a specific safety control against the cost, the time, and the effort required to implement it.
Right. Now, let's get practical here. How do you stop, say, a project manager under pressure from citing SFA and claiming that an essential safety upgrade is maybe too expensive or grossly disproportionate just to save money or meet a deadline? Where's the line drawn that stops commercial pressures from overriding genuine safety needs?
That is the absolute critical question, and it's where SFR differs significantly from a simple cost-benefit analysis. In a pure cost-benefit world, if the dollar cost of the safety improvement is higher than the calculated statistical cost of a potential accident, you might argue against doing it. But the legal test for SFARP is much, much tougher than that. It demands a comprehensive understanding of three key things. Firstly, relevant professional standards. Secondly, established industry best practices. And thirdly, currently available technologies. What can be done?
Okay, so it's not just about the money versus the risk value.
Not at all. Let's use a concrete example, maybe something common in signaling. Redundancy requirements. Say you're installing a critical circuit that monitors train separation to prevent collisions. A simple cost-benefit analysis might show that using a single, very high-quality, reliable circuit is statistically safe enough. The chance of failure is tiny. But SFARP, informed by decades of industry best practice and the catastrophic consequences of failure, demands dual redundancy. It requires two independent circuits monitoring the same function, maybe even designed by different teams using different technologies. Because the consequence of failure, a train collision, is utterly unacceptable.
So the cost of installing that second redundant circuit might be significant, maybe doubles the cost for that specific function, but the reduction in catastrophic risk is considered massive.
Exactly. The legal test essentially says, if a safety measure is technically feasible and its cost is not grossly disproportionate to the safety benefit gained, particularly the reduction in catastrophic risk, then you must implement it.
Grossly disproportionate. That's the
It is. In our redundancy example, the cost of that second circuit, well, maybe 50% or even 100% more expensive than the first for that function, is considered negligible, almost irrelevant when compared to the potential billions lost and the lives endangered by a catastrophic collision. The risk reduction is so immense that the cost is clearly deemed not grossly disproportionate.
That distinction is vital. Simple cost-benefit might say a $10 million upgrade cost outweighs a statistically calculated risk valued at $5 million in potential damage. SFARP says no, if that $10 million prevents a credible catastrophic failure scenario, it almost certainly must be done, unless the cost is truly astronomical, like bankrupting the entire railway for a minuscule risk reduction.
That is the practical application precisely. SF8 mandates that you adopt the state-of-the-art solution, or at least well-established best practice, unless the expenditure provides only a tiny, marginal, or negligible gain in safety compared to the cost. It effectively prevents both underinvestment, where obvious safety improvements are skipped for cost reasons, and it also ensures continuous improvement by forcing engineers to constantly look at new, feasible safety technologies as they become available. Your role as the engineer or the assurance professional is to provide the objective evidence, the hazard log showing the risks, the risk matrices, evaluating them, the options analysis, comparing different controls, all demonstrating that this rigorous SFA PIRP assessment has been done correctly and the justification is sound.
Okay, so SFAP is the core philosophy, the guiding principle. Now let's look at how this philosophy is actually implemented within the life cycle of a typical railway project. You mentioned the life cycle approach before. How does SSA work to embed those safety requirements right from the very first glimmer of an idea for a project, rather than, trying to bolt safety on at the end?
Yeah, the life cycle approach is really the backbone of putting SSA into practice. It operates right through the complete system life cycle. starting at the initial concept through design, delivery, construction, commissioning, then into operation and maintenance, and even covering major modifications and eventual disposal or decommissioning.
The whole lifespan.
The whole thing. And the fundamental goal, as you said, is embedding safety requirements from the absolute earliest planning stages. Because trying to patch safety onto a system that's already substantially designed is always inefficient, it's usually much more expensive, and frankly, it's often less effective than building it in from the start.
So how do the safety requirements actually evolve through those phases?
Well, you can track their development. During the early concept stage, we typically conduct something called a preliminary hazard analysis, or PHA. This is where we identify the big, obvious potential dangers associated with the project idea.
Okay, the high-level stuff.
Exactly. That PHA then directly informs the high-level functional requirements and, critically, the top-level safety requirements that define what the system absolutely must do to be safe. As we move into detailed design, these high-level requirements get decomposed, broken down into very specific safety requirements for individual bits of hardware, pieces of software, and even operational procedures for staff. Then, during delivery and construction, verification activities kick in. This is where we check and prove that we actually built what the design specified. Finally, commissioning requires formal safety sign-offs and validation activities, demonstrating that the entire integrated system is safe to introduce into the live operational railway environment.
You know, that structure, concept, design, build, test, it sounds very familiar to anyone involved in systems engineering in general. So is SSA essentially just the safety-focused track running in parallel with the core systems engineering methodology?
Absolutely. That's a great way to picture it. SSA integrates pretty much seamlessly with established systems engineering practices, particularly the V lifecycle model, which is very common across all safety-critical industries, not just rail.
The V model, right?
The V model provides that necessary rigor because it ensures safety requirements are developed right alongside the functional requirements, what the system needs to do. Safety isn't treated as some separate secondary phase you worry about later. It's integral from day one.
Okay, let's use that CBTC integration example again to illustrate how the V model specifically handles the safety assurance part.
Yeah.
What's happening on the left side of the decomposition phase where you're breaking things down?
Okay, so on the left side of the V, you start with that high-level requirement. We mentioned something like the system must maintain safe headways and separation between trains at all times. The SSA process ensures that this single functional requirement gets rigorously broken down into specific, verifiable safety specifications for all the subsystems involved.
So getting really specific.
It's extremely specific. It means decomposing it into things like, number one, software safety requirements. What's the maximum acceptable latency for the radio link? What specific safety integrity level, or SIL, must the braking algorithm software meet? Number two, hardware redundancy specifications. How many redundant processors are needed in the control unit? How often must the vital safety circuits perform self-tests? And number three, operational procedures. What exactly must the train driver or the control center signaler do if the primary digital communication link fails? Every single piece of that CBTC system has to have clear safety requirements attached and, crucially, traced back to that core hazard of loss of safe separation.
Okay, so that's the designing it right part. Then the right side of the V model is where you prove you actually met all those detailed safety specs you just defined. How does SSA leverage those verification and validation phases?
Yeah, the right side of the V is all about generating that objective evidence we talked about earlier. Verification activities aim to prove that the system or its components were built correctly according to the specification.
Checking against the blueprint.
Precisely. For software, this involves extensive testing, things like static code analysis, dynamic testing, looking for errors. For hardware, it involves rigorous factory acceptance testing, or FAT, before it leaves the manufacturer, and then site acceptance testing, SAT, once it's installed, to ensure components meet their required safety integrity levels, SILs.
Oh.
Validation, then, is the ultimate test. Does the system as a whole actually perform safely and meet the user's needs in the intended operational environment? This often involves comprehensive simulation, sometimes using hardware-in-the-loop setups where real hardware interacts with the simulated environment to test failure modes. And of course, it involves controlled field testing on the actual railway.
And the documentation for all this?
SSA demands formalized safety cases at various key stages of the project. These documents capture all this verification and validation evidence, progressively building confidence. It culminates in the final operational safety case, which essentially acts as the formal license to operate that confirms the system is SFARP.
Now, given that we identified interface, risk the boundaries between different organizations and different technical systems as maybe the primary persistent challenge in modern rail safety.
Hmm.
SSA must provide some pretty rigorous tools specifically for managing those boundaries, right?
It absolutely has to, yes. Modern system safety relies incredibly heavily on formal interface management. SSA provides both the organizational structure and the required documentation templates to ensure there are no safety-critical gaps when different systems or different organizations' operations intersect.
How does that work technically versus organizationally?
Well, for the technical interfaces, say, between the signaling system and the rolling stock braking system, engineers rely heavily on documents called Interface Control Documents, or ICDs. SSA mandates that the safety requirements defined in these ICDs by both sides must be compatible, consistent, and non-contradictory. They have to talk to each other correctly. For the organizational interfaces, maybe between the maintenance contractor responsible for the track and the train operator running services over it, SSA requires formal safety interface agreements. These explicitly delineate who is responsible for what, especially during critical operations like coordinating emergency responses or managing safety during planned maintenance outages when part of the system might be degraded.
And this formal interface management framework, is that what makes interoperability even possible? When you have operator A's trains running on infrastructure manager B's tracks, maybe even across borders.
That's absolutely correct. True interoperability relies fundamentally on this principle. It requires that the safety cases developed by operator A for the safety of their train design and operation, and manager B for the safety of their track signaling and infrastructure management are rigorously coordinated and demonstrably compatible with each other.
They have to align.
They have to align. SSA provides the mechanism for assessing those complex cross-organizational risks. If, for example, the braking curve assumed in operator A's train safety case is incompatible with the signaling headways provided by manager B's system, the coordinated SSA process must flag that incompatibility long before that train ever attempts to run on that track. It demands a coordinated solution is found and assured.
Finally, looking ahead, SSA can't be a static process, can it? The threats are constantly evolving. We've talked about cyber threats. Climate change impacts are becoming more apparent, and there's always new technology emerging. How is the framework itself preparing to assure technologies that are radically different from anything built even, say, 20 or 30 years ago?
No, it absolutely cannot be static. SSA is, by necessity, a living framework that has to adapt, sometimes quite rapidly. And we are seeing major assurance shifts happening right now. Think about autonomous train technologies, for instance. They fundamentally changed the definition of system failure and recovery.
How so?
Well, where previously a human driver could potentially intervene or mitigate a failure, a fully autonomous system must prove its own intrinsic integrity to a much higher level. This requires developing complex new methods for the assurance of, say, machine learning models used for perception or decision-making. We need to ensure their thinking is transparent enough, auditable, and inherently safe under all credible conditions. That's a huge challenge.
Definitely.
We're also seeing the widespread integration of technologies like the Internet of Things, IoT sensors, monitoring track condition, bridge strain, weather impacts, and the use of big data analytics across the network. This technology offers the potential for a really massive shift in safety management.
Which is?
Moving beyond just reacting to incidents after they happen, towards genuinely proactive risk identification and mitigation. It's the shift towards predictive safety.
That sounds like the most exciting development, maybe especially for the next generation of engineers coming through. If SSA is the structure, how will it be used to actually validate and assure these potentially powerful AI-driven predictive systems? Can we trust the predictions?
That's the million-dollar question. SSA will be the framework that ensures we can trust those predictive warnings. If an AI system predicts, say, that a particular section of track has a high probability of developing a critical flaw within the next 72 hours based on sensor data, well, we must assure the integrity of that prediction itself.
How do you assure a prediction?
It requires several layers. Rigorous validation of the AI model itself, how accurate is it? Assurance of the quality and integrity of the sensor data feeding into it. And, critically, assurance of the business process that receives and acts upon the AI's warning. What happens when the system flags a potential issue? It demands a whole new category of safety case, the data-driven safety case. This move, though complex, dramatically accelerates our ability to achieve SFAP by enabling almost continuous real-time risk reduction based on foresight, not just hindsight. #tag outro.
Wow. Okay, that was a Really comprehensive look at system safety assurance. We've established pretty clearly, I think, that SSA is far more than just regulatory compliance paperwork. It's really the living governance system that connects those fundamental legal duties, that core commitment to achieving SFAAP, to the rigorous technical implementation that happens across the entire system lifecycle. It provides the consistency, the harmonization across different players, and the scalability that's absolutely required in the vast complex environment of modern railways.
And I think for anyone listening who's entering this field or maybe early in their career, understand this practical takeaway. SSA is effectively your professional currency. It's the language you must use to argue for technical decisions, to justify the resource allocation needed for proper safety measures, and to structure the management of those incredibly complex organizational and technical interfaces we discuss.
Right.
Your primary role, really, as a safety-focused engineer or manager, is to be the custodian of that objective evidence. You're responsible for gathering, managing, and presenting the documentation that proves, beyond reasonable doubt, that the railway system is safe to operate.
So, as we increasingly integrate these powerful new tools, AI, IoT, big data analytics into these safety systems, fundamentally shifting perhaps the cost structure of implementing advanced safety improvements, we leave you, our listeners, with one final thought to maybe mull over. If state-of-the-art predictive technologies start offering near-perfect certainty about identifying future risks, but integrating them requires exponentially higher investment than traditional, maybe more manual inspection and monitoring methods. Does SFA, that reasonably practicable principle, now mandate that the industry adopts these potentially very expensive high-certainty systems?
That's a fascinating question.
And if it does the pursuit of true predictive safety force the industry to completely redefine what reasonably practicable actually means in this new technological era, potentially forcing many traditional assurance methods to the wayside? What new ethical and engineering challenges will that create for the safety assurance professionals of tomorrow?